Sure. So I hope you can see my screen, right? Could you confirm that?
Yes, sir.
अच्छा और दूसरा ये है कि जो चैट विंडो में आप अपनी वो भी लगा दिया अटेंडेंस, ठीक है? बाद में मैं दोबारा बता दूंगा. So let's get to the slides. Okay. So this was our conclusion from the previous lecture. So if I remind you something we did in the continuous time. So for a continuous time system, if you can remember that when you have an LTI system and you um, at the input you give this special signal, which is the exponential signal. So it turned out that because of the LTI-ness, all that can happen to the signal at the output is there is no change in the in this shape. It is still exponential, but there is a multiplication of some complex uh, quantity, and we identify that as our transfer function, yeah, or system function. Some people call it system function, some people call it transfer function. A similar thing happens with discrete time systems. So if you have an LTI discrete time system, it turns out that um, and that is why we were calling it the eigenfunction. That exponential was the eigenfunction. So it turns out that for a discrete time system, this function z to the nth. Now z here is a complex variable, and n is the n discrete time. So if you follow a similar reasoning for LTI, it turns out that that shape Zn doesn't change. The output is of the same form, and all this system does is to multiply this by a complex scalar, and that is what we will call the transfer function or the system function, right? So h of z for discrete time systems, h of s for continuous time systems. Okay. One common misconception at this point is that when we are using the symbol h, for example, for the transfer function, and I say, oh, h of s is for continuous time and h of z is for discrete time, this doesn't mean that we are talking about the same system, okay? Many students get this wrong. They think that, oh, we start from h of s and we replace s with z. No, that is not what we are doing. Because we are talking about another system, LTI. It's just LTI, and although we are using the same symbol, but a completely different thing, right? So, I mean, if we had these two topics on the same page, for example, we would never use the same symbol H. We could call them H1, H2, or something like that, yeah? Or maybe we could say H um, discrete time and H continuous time. Yeah, you will need some labeling for that. Normally, we don't need these labelings because these are different chapters, different contexts, things like that, right? And when that happens, the next question is what is this h of z, right? So because we know LTI will involve convolution, so actually you will be convolving something like h of n will be impulse response, and when you work this convolution out, you know how to convolve. It turns out that this h of z is simply this sum, and this sum, if you think about it carefully, it is just the z transform. So z transform actually arises naturally, from this analysis. And what that means for us is that if we can start with any signal x and we express this as a linear combination of these special functions, right? Uh, and we apply it to an LTI system, right? The output will be of the same form. So it will have the same functions, yeah, z to the nth, and that combination ak is not going anywhere because it's a linear system. This summation is not going anywhere because it's a linear system, and because it is an LTI system, so this multiplication by the system function will also be visible in the output. So it's very similar. Yeah, if you compare it with the continuous time, what you see there is that okay, if you apply exponential st, let's say it is skt, right? The kth variable x s, so it gets multiplied with h of s and ak and sigma k, and that is your y of t. This is what we saw in continuous time as well. Okay, so now we are finally ready to start the Fourier series for discrete time systems. And the motivation for that is this, right? Um, we want to see whether we can express a signal in this form. Now, this is if we start this directly, that's too complicated. So let's simplify this first. So this z we know is a complex number, right? So z is a complex number, which means that it will have a modulus, the absolute value, magnitude, whatever you call it, and it will have some. We can write it in the polar form, right? Uh, it will have some argument, right? Let's call it, um, yeah, theta or whatever. You can call it theta or anything. So this is the magnitude. So if you represent this in a circle, this will be the radius of that circle, and then the theta is actually the angle. Yeah, so you can be on that. So for simplicity, let's assume that this modulus will be 1, right? So all that can happen um, is the angle. Angle can go from 0 to 2 pi, then 4 pi, so on and so forth. So when that happens, so instead of a general z, we are looking only for a specific z. And if you look at the specific z, this is just the exponential, the complex exponential. So we'll have a cosine theta and a sine theta, and then you can have this j. So this part 10 of these slides, discrete time Fourier series, it is trying to achieve that. The goal in this chapter will be to start with the signal x in discrete time and express this signal x as a linear combination of these functions, right? These functions. Um, and here you will have some coefficients. So if you can remember this motivation, the topics will be very easy to digest. So
Sir,
yes,
sir, I have a question.
yes.
Sir, why does discrete require an angle like in the continuous?
Why does discrete require
An angle?
an angle?
Yes.
No, the angle is required not because of discrete, but because of the complex numbers. Every complex number, right? When you have a complex plane and you have a complex number. So there are two ways to express that. Either as these two components, the rectangular components, right? X, Y. If you write it in this way, then you don't need any angle, right? But if you want to express this in this way, where you have this distance from the origin and the angle, so you have this angle, right?
Okay, sir.
And that
Thank
same
you,
thing
sir.
can be said about the exponential st as well. If you go to continuous time, you have exponential st. This s is complex, right? When this is complex, this will also be able you'll also be able to express this as the magnitude of something, and yeah, the angle, right?
Sir,
So
this angle basically represents the phase
yeah, it's the
shift
phase. Yeah,
of
yeah.
the
We are
signal.
using the word angle, but a better word is phase, right? And even phase is not a good idea. More appropriate is argument, right? Yeah, argument, modulus, and argument. The reason I'm not using the word phase is that phase has a problem, and you should recall something from physics, right? When you are using the word phase, it can go on, it can cross this 360 degrees and it can then continue. So a phase can go beyond 2 pi, right? You can have 4 pi, you can have 8 pi, but the argument is defined to be between minus pi and pi, right? And this is what we typically do. So let's now introduce the Fourier series. So because now you have this background, so you will understand everything in these points. So you need the Fourier series, which is simply a representation of periodic sequences. This is because we have discrete time signals, so we will have periodic functions, and there will be sequences. And with the Fourier series, we will express a sequence or a discrete time signal as a linear combination of complex sinusoids. This is exactly what I told you, complex sinusoids. Complex sinusoids is of this form, right? And remember, the magnitude is 1, right? Otherwise, you cannot call it complex sinusoids. If the magnitude is not 1, what will be a better name for this? Let's say I don't require this to be 1, right? I want this, I can allow this to be larger than 1 as well, or smaller than 1. So how will this name change then? Hmm? So let's say I have this thing, yeah, 5 by 3. Can I call this complex sinusoid? Hmm? Because here I can have reals, yeah, I can have actually we need time here, right? We need time. So you have this real coefficient, let's say half t, right? And there is complex. So this will be complex exponential. We will call it complex exponential. When you say complex sinusoid, you want this to be 1, right? So and why we need that, I already told you. It's because of this property of LTI systems, that the eigenfunction or the eigensequence is of this form, right? This is an eigenfunction.
Sir, but when we find the coefficients and when they get multiplied with them, then this becomes the complex exponentials.
No, but they are constants. If they are constant, the thing is that I started with 3. Yeah, that was not a good example. Uh,
Yes.
yeah, this is actually when you have exponential and this t. And let's stick to n, discrete time. So if it is n here, and if it's, let's say, 2n here now. Now this is real exponential, right? This is complex sinusoidal. So real exponential multiplying complex exponential. No, sorry, real exponential multiplying complex sinusoid gives you complex exponential, right? This is now complex, and that cannot happen in this linear combination, right? Look at this again. Yeah, when you set this z to exponential j theta n, yeah, these things do not depend on time. Yeah, that is why we call them LTI. Yeah, LTI means that the only variation will come from the signal, not from the system. You get that? So
Yes.
let me draw a diagram and you will understand this better. So if I have an LTI system, right, and I supply this signal, for example, now the variation is this one, and now the output may be, yeah, I mean, even if I have a combination, let's say this is the combination, theta k and sigma k and sum over k. So here you will have these same exponentials, complex sinusoids, and this ak will get multiplied by h, yeah, k maybe, and then summation. Now this hk cannot depend on time. If it depends on time, then it cannot be LTI, right? This may still be linear, but this will then be a linear time varying system, right? So there is no, because these coefficients must be constant. That's why we are calling this an LTI system, and that's why we can still use the word complex sinusoids.
Okay, sir.
So if you remember, because this is Fourier series, so we should recall certain things from continuous time Fourier series. If you remember, there we saw something, that when we were combine those sinusoids, right? The frequencies of those sinusoids, like we were using this omega k, right? So we saw that those frequencies must be multiples of a fundamental frequency. Yeah. Because otherwise the sum will not be periodic. You remember, the sum of two sinusoids is only periodic if the frequencies are related in a specific way. There must be, the ratio must be a rational number. So we need similar requirements here, right? They're called harmonically related complex sinusoids. So a set of periodic complex sinusoids is said to be harmonically related if there exists some constant. Now this constant, if you think about it, it looks very similar to 2 pi by t, remember? And that was our omega naught, if you remember. So this will be our omega, capital omega naught. This is our discrete time fundamental frequency. So yeah, said that the fundamental frequency of each sinusoid is an integer multiple of this, just like k times omega naught. Yeah. So we wanted in continuous time, we wanted our frequencies to be of this form, which is k times 2 pi over fundamental period. So in this case, our frequencies capital omega k should be of this form, k times omega naught, and omega naught should be 2 pi by capital N, right? So only when these sinusoids are harmonically related, only then you can combine them to get a Fourier series. So if you have now a set of harmonically related complex sinusoids, and to have a simple notation, we don't want to write this horrible thing every time, remember? So you must realize that this thing in the bracket is actually capital omega naught, the fundamental frequency, and this k is because you have the kth integer. It is this k, and discrete time is n. Yeah, so that n is there. So now writing this phi k is much simpler than writing this whole thing. Okay, so only n elements are distinct. Now this is the thing which was not there in discrete continuous time. In continuous time, all the frequencies were different, and every time you get a different sinusoids there. But here, because of the discrete time, you have this periodicity. After some value of n, they just get repeated. We saw this example last time, yeah, where because of this discrete time, you can't have more than a few frequencies, and then things start repeating. Um, so there will only be a maximum of n distinct sinusoids. So this summation, that is why this summation, although you will write k from minus infinity to plus infinity, but because these terms are actually repeating, so when you take the combination, then you will not have this infinity anymore because you just combine them. So the overall sum will look something like this, right? It will look something like this. And if you remember, I showed you this notation that whenever you see this n in the angle brackets, it is just a periodic sum, right? That you sum just over one period, yeah? It denotes summation over just one period. That period can be 0 to n minus 1. It can be 1 to n. Yeah. Do you remember these dots? Why do we use these dots? Anyone? These two dots?
From zero,
Continuation.
Sorry? Say
from
again.
0 to n minus 1. That's why we
Yeah,
use
yeah,
it.
but why do we use the two dots? What if we do, what if we use comma? What will that mean?
Then
Pair.
No, we know pair is a different thing, right? We because we use this notation for intervals, right? So if I write this a comma b, this is continuous time interval, right? So this will be all the real numbers between a and b. And when we use these two dots, it means only integers, right? That is what you need to remember. So if I use, for example, 0 to 5, and if I put a comma there, it means the real line segment between 0 and 5. It will include everything in between. But if I use these two dots, right, that means only the integers, right? So if when we achieve this, let's say you are somehow able to express this discrete time signal or sequence as a linear combination of these. Remember, these are the sinusoids which we were talking about, and they are not just complex sinusoids; they are harmonically related complex sinusoids. Why? Because the frequency is an integer multiple of this thing. That's very important. If I don't do this, then they will not be harmonically related, and they cannot be the linear combination may not be periodic. We need periodicity in all cases. So when you do that, then you have a Fourier series, and that will be called the discrete time Fourier series, and these coefficients are called the Fourier series coefficients, but dt Fourier series coefficient. And this is how you will express this symbolically, right? Rather than writing that whole thing every time, you just write the discrete time signal on the left side, the coefficients on the right side, and you just write dtfs, right? And if I, for example, write instead of dtfs, if I write ctfs, then this will be x of t, the continuous time signal, yeah? And ak, just like you had in the exam. Now, how do you compute these coefficients? It's a similar thing, right? You need to extract these coefficients, and for that you just multiply this by some exponentials, and the multiplication should be such that you have this orthogonality, yeah, just like you extract coefficients of a vector. So you need to multiply by the complex conjugate, remember. So make sure you see the conjugate thing here, right? The conjugate. So you start with the discrete time sequence and you multiply this by the complex conjugate, yeah. So if remember, if that thing, if this thing was phi k of n, right, this thing is actually phi k star of n, the complex conjugate. And the cool thing about complex conjugate is that when they get multiplied, this x of n will have all these, this complete sum. And when this sum gets multiplied by this thing, because of orthogonality, all the pairs will become zero, and only one of them will survive. Yeah, the one which is not orthogonal. And this is how you extract your coefficients.
Sir, actually, because of the orthogonality, the one with the same frequency
Yes,
that becomes constant, and the
that that
other
that
ones,
that, that becomes non-zero. Yeah,
yes,
every other pair is orthogonal, so you get zero, right?
the every other pair has again some frequency, and when we integrate them over one period,
Yes,
since they are sinusoids, then they are cancel out because the area
and
is
because
plus
we
and
are,
minus.
yeah, here we are using summation. Yeah, this is not integration. So
No,
whether
sir,
you are
but
using,
in the x we do the integration, na? X
yes,
of
yes,
n.
yeah. So
Then
what you need to remember is this thing. What you need to remember is the orthogonality, right? So when you use orthogonality, it doesn't matter whether you integrate in continuous time or whether you take the sum in continuous time. Orthogonality means that uh, the sum or the integral will be zero, right? And it will only be non-zero when they are identical. So the easiest way to remember it is this way. Let me show you on a separate page, because there are some quick ways to remember these things, and I'll share you one. The way I make sense of this is, you know, you have these three components, yeah, ijk, right? Ijk. So you have vector, yeah, v1 I plus v2 j plus v3 k, right? Three components. And if you now multiply this with another vector, right? Let's say, let's say I want to extract this component. So if I now multiply, if I now take the dot product with this one, right? v1I, only this one will survive. Yeah, it will have a zero dot product with everything else. So every time you just take that particular component and everything else becomes zero.
Yes.
And you will also remember why we use this word orthogonal. Yeah, why not perpendicular? I told you in the class. Can you remember that? Why do we replace perpendicular with orthogonal? Because what I told you here is perpendicular, right? So why do we
Yes,
need to coin a new term?
sir, because uh, the orthogonal vector is perpendicular with every vector in the
Yeah, but then you
respected
can use
domain,
perpendicular. But then
respected
you can use perpendicular.
I, j, or k. No, sir. If one vector is orthogonal to the other vector, then the I component of that vector is perpendicular to its I component, the other vector's I, the j component of another vector.
Yeah, but that is if that was the only reason, then perpendicular is perfectly fine. Yeah, I
Uh,
is perpendicular to j is perpendicular to k is the reason we use this new term is that we don't want to stick to vectors only. We want to use this idea to functions with functions as well. Yeah, and we want to do it in n dimensions. Perpendicular only makes sense up to third dimension, right?
okay, sir.
When you have more than three dimensions, there is perpendicularity is meaningless, right? So that's why we need new names, orthogonal. You can use orthogonal for any mathematical object. So you can have one data set, yeah, and another data set, and you can speak of their orthogonality. Okay, so instead of memorizing this formula, remember, and why do we need this thing? Because then we need to take the average as well, right? Just like we had this 1/t in continuous time. So what you need to make sure is that this, you need to remember this minus sign. That is without this you will not have this orthogonality. And yeah, and because it is discrete time, so this function will this sum will actually be finite. You don't need infinite sums here. And yeah, once you have this, you can now investigate the properties. The properties are very similar, right? Linearity and translation. And if you look at these properties, they're very similar to what you had in continuous time, right? And this one, yeah, this one property in the textbook, in every table there is this problem, yeah, and that is why I had to get that corrected. Uh, this odd and even, unfortunately, is only for real. So this was actually J, yeah, J A, because when it's pure imaginary, you first have to turn it into real, and then you can speak of odd and even. Only this textbook has this problem. Or the other books, they don't. They remember this thing. And here are the proofs. I don't want to go into proofs. And sometimes he will be using ck, sometimes he will be ak. So you're not going to get confused by that. You just declare your convention. So if you say, okay, I will use ak for the coefficients for the discrete time Fourier series coefficients, then you are fine. Yeah, nobody can dictate you to use C or A all the time. So it's purely based on convenience.
Sir,
Yes.
could you please make some physical, intuitive sense of modulation, a comparative analysis of both in continuous time and discrete time? Like, how is the Fourier making
Oh, do
sense
you
for both?
remember? Do you remember modulation as I told you in continuous time? Because you only need to understand it in continuous time. The discrete time is very simple after that. So could you recall if this was, let's say, continuous time modulation? I told you once in a lecture, although this is a topic of analog and digital communication, right? But this is just if you think of this as a um, periodic signal, right? Because this is a periodic signal. So this will have its own spectrum, right? Yeah, every periodic system, every periodic signal will have a spectrum. By spectrum, we mean that, okay, I have this much frequency, I have this much weight for this frequency, this much weight for this frequency, and so on and so forth. So when you multiply, because modulation is simply multiplication by a complex sinusoid. So when you multiply, um, you're just, let me just show you a graph, okay, in continuous time. Let's say I have this signal in time, okay, and this is periodic, right, and so on. And if I now multiply this with a very high frequency sinusoid, and I'm just plotting one of the components, let's say this is the cosine. I will I will have a sine as well. So when I multiply these two, look what happens. Because this is high frequency and this is low frequency, right? So this low frequency signal will just appear. So can you tell me the amplitude of this high frequency signal? It's constant, right?
No constant.
The amplitude is constant. So when we multiply these two, you will see something like this. This is something you have seen in electronics probably, right? So I can now draw a signal. Yeah. So it's that same high frequency, but with a different with a time varying amplitude, right? And where is that time varying amplitude coming from? It is coming from the low frequency signal. So that is what we mean by modulation. Modulation means that you use a low frequency signal to modulate the amplitude of a high frequency signal. So, so the high frequency signal is just like a strong, yeah, I would say maybe donkey, yeah, and this low frequency is maybe some weak, yeah, old man, for example. And the old man is sitting on the donkey. The donkey only knows how to walk fast. It has no other purpose, but the old man wants to ride the donkey. Yeah. Yeah. So this is how you send signals in space. If you send low frequency signals, they will just get lost. So you pick a high frequency signal, right? And then you just make the amplitude of that high frequency signal depend on some low frequency signal, and yeah, then you just send it off, right?
Okay, so now it's just the same thing, but with on discrete
Yeah, yeah.
timestamps.
No, and you must be able to tell me why we need to understand all of these things in discrete time. Why was continuous time not enough? You should remember that.
Because aren't there just too many timestamps to remember? Then, like if we're sending data, discrete would be only the most important frequencies, most important timestamps.
Yeah, that is partly correct. The thing is that if we want to stick with analog continuous time, then we have to implement everything in continuous time. Yeah, then we'll have to do
Mm,
analog electronics. That is not practical. So we want everything
yes,
digital. So whenever you want to use computers for solving a problem, then you have to discretize everything. Yeah.
yes.
And the reason we want to use everything discrete is not for show off, but because in computing you can fix your errors. In analog, there is no way to fix your errors. You wouldn't even know what is happening. So here, for example, I can just give you a very simple example. Let's say I choose this signal. Let's say this is my 1 and this is my 0, right? So if I send this off and analog, and at the receiver, it is something like this. I don't know whether it's a 1 or a 0, right? So, but if I turn this into digital signals, this complete signal will be represented in ways that can be actually recovered. You can actually recover your signals if you are using ones and zeros. But if you are relying on the analog signal, then there is no way to recover it. So we need discrete time, right?
Sir, all the properties in the continuous time are understandable, but the last periodic convolution and the multiplication properties, they don't make any
You
intuitive
you
sense
mean you mean in discrete time or a continuous time?
in continuous time, sir.
You don't understand the property of continuous time? This is the table of properties, yeah. So what you are telling me that you don't understand this thing, this one?
Sir, yes, sir, this periodic convolution and the multiplication property.
Okay. I told you why this will be a periodic convolution. Because if I replace
Yes, sir.
this with convolution, what will happen?
Sir, because since the signals we are taking are periodic for the Fourier series, and when we convolve the periodic signals, they have infinite energy.
Yes, this will not exist.
That's yes, sir.
This will not exist. Yeah. So when this doesn't exist, then the Fourier series will also not exist. Yeah.
Yes, sir.
So you need to, and why is that happening? Because of periodicity. So you just restrict your calculation to one period,
Yes, sir.
and that is what you mean by periodic convolution, right?
Yes, sir.
So it's just necessary. You don't need to, yeah, remember it. That's the only thing you can do. You can do, right?
Yes, sir.
And now
Yes,
here is a
sir.
simple, yes,
Sir, actually, my question is that um, from when we change the signal from the time domain to the Fourier domain, na,
yes.
then we can make the intuitive sense of the translation and the
So you mean
modulation. But
you can't make sense of this?
yes, sir.
Yeah,
From
but that is easy. I'll tell you. That is easy because if it was let's say if it was not periodic, right?
yeah, sir.
So you will have a similar property in Fourier transform. It's much easier to make sense of this in Fourier transform, right? So if I now go to Fourier transform, because you know the link between Fourier transform and Fourier series is very easy, right? You just restrict it to one period. uh, yeah, so you should be asking this question, right? Time domain, convolution in time domain, multiplication in frequency domain. Because if you understand this, that is exactly what is happening there. In periodic functions, this will become periodic
Periodic convolution.
convolution, right? And these becomes your coefficients, right?
Yes.
And then there is this margin. So now, do you remember why this happens? Why do we multiply when we convolve here? This actually is exactly uh, another way of something which you already know, right? I just showed you something a while ago, and that is this. What was special about the exponential? It was the eigenfunction, right, of LTI.
Yes, sir.
Yeah, so that LTI appears there, right, with something like this. So when you take the and you can now replace this S with j omega if you want, right? Right, j omega, and in Fourier series you will have j k omega naught. Yeah, so they are all those eigenfunctions things. So now, when what think about it, when you take convolution, you are convolving two things, right? And when you are convolving two things, actually you can pretend that one of them is an LTI system, because the convolution is something which the LTI is doing, right?
Yeah.
And because you know the output will be of the same form, so the form is not going to change. So all you can do is to multiply by that transform. So that is why you see the multiplication, right? So this multiplication You can think of one of them as the transfer function, right? Think of this as the transfer function, and this is the transform of the other signal. So a better way of looking at this is, instead of thinking in terms of x1 and x2, think of it in terms of h star x. So x is the signal, h is the impulse response, right? So you should have no problem understanding this now. Is this clear?
Yeah, sir.
Yeah. So remember LTI-ness. It's all because of LTI. Okay, so let's go. I'm skipping all these things now. Um, Conjugation, duality. Yeah, in discrete time, you also have this duality property, right? That if you have a signal on the x-axis and the coefficients on the left side and the coefficients on the right side, and you swap them, yeah, you bring that function, that mathematical form, as you turn this into a time domain signal. So you see, it's very similar to the duality we had for Fourier transform. You have this minus sign and, yeah, 1 over n, and you can prove all these properties if you want: periodic convolution, multiplication. And the reason you have multiplication turning into periodic convolution and periodic convolution turning into multiplication, this is also because of duality. Yeah, because you bring the multiplication to the left side, so the convolution has to appear on the right side, and then you have these Parseval's relationships. I would highly recommend that you don't use this equal sign, yeah, because this equal sign is misleading. You should use belongs to, yeah, because you can think of this as a set. Think of this as the set of values over one period, So you can think of 0 to n minus 1, yeah, or any other period, even odd symmetry. And because these can be complex, so remember something which I keep telling you, that yeah, when this only makes sense when x is real. And when it is not real, then you have to use complex conjugate instead of that. Conjugate symmetry. Yeah, conjugate symmetry. Yeah, he has already used this. This is the term which you should be using: conjugate symmetric and conjugate antisymmetric. So conjugate symmetric will replace even symmetry, and conjugate antisymmetric will replace odd symmetry. And you can have this trigonometric form yourself. That is just a repetition. We had this. Yeah. So now let's recap. What we had was this. So yeah, let me just show it here. What we had was a discrete time signal, and our goal in discrete time Fourier series was this. We wanted to express this as a sum of these exponentials, right? I can simply write that phi k, right, instead of writing that horrible expression every time. And I'm writing ak, and this k is just over one period. So just I'm writing n, capital N, in the angle bracket, and k belongs to that one period. When I say one period, I mean the set of values of small n, small k, which span only one period. And to get these coefficients ak, you need a formula which is 1 over n sum over one period again. This time it will be n, because you want to get here you want to get rid of k, and here you want to get rid of n, and it will be x of n phi k of n and this complex conjugate, right? So now what you need to do is this. For some reason, um, yeah, there's this thing between physics and engineers. They have different conventions. So what one of those groups actually decided to bring this 1 over n here. They want to have this 1 over n here. Sorry. So I'm just now crossing it from here, and I'm bringing it there. But then, yeah, if you want to express x of n in this way so that 1 over n is here, then the 1 over n disappears from there, and then this thing, you cannot call it discrete time Fourier series anymore, right? So the name changes. Then it is called discrete time Fourier transform. Discrete Fourier transform, sorry, not discrete time. So that was discrete time Fourier series before, discrete time Fourier series, and now it will be discrete Fourier transform. Yeah? So all you have to do is this, right? That 1 over n is here, and it disappears from there, and you have a new definition. That's not the only thing that is happening. And now skipping all these derivations. Uh, so one thing which you need, let me take you back to that formula. What you need to remember in this, sorry, let me go to the original definition of discrete time Fourier series. Yes. So when you see this, you have a discrete time signal and discrete time Fourier series and these coefficients, and you can have it for another one. What you must remember that because we are using the word Fourier series, this must be periodic. This must be periodic, right? And yeah, the k, although k can span the entire integer line, but essentially only some of them will be repeating forever. So in discrete Fourier transform, we do two things. One is something I already told you. Yeah. So one is this thing that we bring the 1 over n to this side and we remove it from there. But there's another thing we want to do. We don't want this periodic thing and it keeps repeating, that makes things so complicated. So we define these two transforms, yeah, just for this one period. And we say, okay, instead of saying that it will be repeating outside this, we say, okay, it doesn't exist. Yeah. So in calculus, can you recall there is an operation in calculus? Let me just, let's say I have this function, yeah, sine function. And let's say I remove this. I only keep it for one period. And instead of saying that it's 0, I say that it will be undefined. So what name is used for this operation? Where I change the domain of a function from the full real line to just this. What is the name of that operation? So I start with a function and I just take part of it and I say that, okay, everywhere else it is not undefined. So what have I done to this function?
Restricted or
Yeah,
restriction?
it's called restriction, right? Function restriction. That's what you do before you can take the inverse, right? You cannot take the inverse if you don't restrict it. So we are doing this restriction here as well, right? So just let me repeat it. We do two things to discrete time Fourier series. One, we bring this 1 over n to this equation and we remove it from there. And the next thing is that we restrict both these equations to this one period. both for small n for small k, because this one involves small k, this one involves small n, and now we have a new transform, right? And that transform is called DFT. So you need to have these two things in mind, right? So how is discrete time Fourier, sorry, not discrete time, discrete Fourier transform, DFT. How is DFT achieved from DTFS? Yeah, so I start from DTFS and I want to get DFT. I have to do two things. I have to bring the 1 over n, right, to this equation, and I'll remove it from the coefficient equation. The equation for these are actually, remember, these were supposed to be your AK, but we are not calling them AK anymore. Why? Because AK will require K to be everywhere on the integer line, but we want to restrict it to this interval, and that's why we have to use a new symbol, and let's call this X of K, right? So this is what we mean by DFT, right? And this will be inverse DFT. So one of them is called the analysis equation, and the other called the synthesis equation. And yeah,
Sir,
yes,
but sir, as far as I can recall, when we were studying 4 year for continuous, the entire idea was to make the period to be infinite so that it never repeats and becomes aperiodic when we go from series to transform.
yes, yes,
So,
yes.
when you're just restricting the domain, basically you're just taking one period. So, if it is already aperiodic, how are you taking just one period? I
No,
don't
no,
understand.
it is not aperiodic. You pay particular attention to how we start. Okay, we start from a discrete time signal, right? And then we work out the discrete time Fourier series, right? And there you have AK, right? So this n can be anywhere on the integer line, and this k can be anywhere on the integer line, and we require this to be a periodic function, right? And now what I'll first tell you the fact, and then I'll tell you why we are doing this, right? So we know x of n has to be periodic, right? We know it because otherwise the DTFS doesn't exist. And now what we do is that we just remove everything and we just pick one period. That's it. Now it has two advantages, right? One is that we have a complete object to work with. So when we store it in a computer, it is the entire thing. Yeah, we cannot say, "Oh, I'm not storing the other parts, and they must be there." But the main advantage is what you said, that we can now apply the concept of DFT even to aperiodic signals. How? Let's say I have an aperiodic signal, right? Discrete time aperiodic signal. Let's say I'm plotting it, right? So, and let's say it's zero everywhere else. So what will I do? I will, instead of saying that it is zero, I'll make it undefined there, right? And I will say, okay, this is my new signal, and I'm making it undefined everywhere where it was zero. Not these zeros. These zeros is in this range outside, yeah, where it remains zero everywhere. So I'm now making it undefined, and now I can pretend that this is part of some periodic signal, and I can use the concept of DFT to this. So this makes it applicable even to aperiodic signals by a change of perspective, right? But that is, I would say, that is not the main advantage. The main advantage is that DFT, when you store it in a computer, it is the entire thing. If you store DTFS in a computer, that will not be the complete package. You have to say somewhere that, okay, I am storing only this because I cannot store the rest of the signal. I hope you get the main point, right?
Yes, sir.
And many of these definitions actually, you might think that we are complicating things, but actually we are simplifying. Let me give you a very simple argument for why we would like things to be undefined, right? So let me just draw a continuous time signal, right? This is a continuous time signal, right? I don't care whether it's periodic or not. That's not the point. And now I use sampling to discretize it. Huh? So what will I do? I will just, okay, let me use different color, right? So let's say I pick a value here, and I pick a value here, and I pick a value here, 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 here. And now I store these values, right? And now I don't have access to the original. Okay. So I have access only to this. Now tell me, is there any way for me to tell what is the value in this region?
No.
Yeah, because I lost the original signal. So what is the best way to say about this? What is the best statement you can make about this region? You will say it's undefined. Yeah. If you use any value, let's say, if you say, oh, it is 0, then you need a reason why it is 0. When you don't know the value, how can you say it is 0, right? So undefined is the best way, right? Because it honestly represents the state of knowledge. Okay. Yeah, Fourier series, Fourier spectrum. Now I'm skipping most of these things because you're you can remember many of these, yeah, line spectra and yeah, spectrum. Yeah. So I don't see any difference here. Yeah, there are some interesting properties that if you happen to know that X is real, yeah, then this has to be conjugate symmetric. But this is something you knew already. But this is not the only thing you can say. If X is real, there are other things which you can, with other observations. Now, this is something which is specific to, now this is a consequence of restricting the domain. So we are now restricting the domain to 0 to n minus 1, right? Now, normally when we say um, uh, conjugate, when we say conjugate, we for example, if I have x of k, complex conjugate would require x of minus k, for example. Yeah, if it is real. No, complement. If I want to say complement, but the problem with this minus k is that if let's say this is point k, and if you say minus k, then you have to come here, and that the signal is not defined there, right? So you lose that property of x of k, reflection. You can't use reflection. So the best you can do is this. Do you remember the concept of two's complement from programming fundamentals? Two's complement.
Yes, sir.
Yeah. So let me remind you. I mean, if you can remember that now, if let's say I have a number between 0 and 100, right? So let's say I'm speaking of 10. Now the normally and properties and previous chapters, I would try to go to minus 10, yeah, like this x of k and this x of minus k thing. Now that is not possible here, right? So what you can do is that instead of using 0 minus 10, you can now say 100 minus 10. So the complement of 10 will be 90 rather than minus 10, right? Because you have to restrict everything to this range, right? It's just like that modular arithmetic. So that is what you will see in these properties. Yeah. So some of these coefficients, if you go from 0 to let's say n by 2, yeah, midway, and then the other coefficients are determined by that part. So you don't need to complete. So for example, from 0 to n minus 1, you don't need to compute all of them. You can just compute it till n by 2. And I have to take the floor because this is not an integer necessarily. And once I compute these coefficients, these are simply computable from this relationship. This is another way of conjugate. Yeah, this is a new concept of conjugate. You can think of it as finite conjugate symmetric, right? If we did not have this problem of restriction, then remember, then you would not have this n. You would have just, yeah. If you can recall from previous lectures, we would have something like this: ck, c minus k, and star. This was our definition of conjugate symmetric. Do you recall that? Ck equals c minus k star.
Yes, sir.
And yes, and,
Yes.
and now we can't have that, yeah, because this minus k is outside the domain. So what do? We replace that zero with capital N, right? And this is what there were two guys who actually spotted this, and they came up with a better algorithm of computing it. I don't know if you have heard this, but if you search the internet, you will see this FFT. The chances are that you have heard FFT before DFT, right?
Yes,
Yes.
sir.
Yeah. The reason is actually FFT is actually DFT, but which is a more efficient algorithm. It is an algorithm. It is not a new definition. It is an efficient algorithm to compute DFT. And what makes it efficient? It actually exploits this property, right? That you can only compute it. Actually, it goes further than that. I just told you the first step. So imagine you have this zero and you have, let's say this is to the 10th, for example. So my first shot will be to save time by computing these, right? And leave this out because I can use that relationship. But then I can go further. I can now start from here and I can cut this down into half, right? And then you can leave this out. So what those two guys did, I don't remember the names, they took it to the extreme and they made this algorithm this was kind of a tree diagram, right? And they came up with a very, very clever algorithm. That's why you see it so often. Just imagine DFT, nobody knows DFT and people know FFT, where in fact they should be knowing DFT because that's the definition. So Fourier series and LTI systems, I think this is something which I have been telling you. Can you tell me why is he using this capital omega here? Hmm? Why not small omega?
Sir, because this is discrete time.
Yeah, this is discrete time, right? That's what you need to remember. And you remember I started this lecture by this observation, right? This told us that z to the nth um, is an eigenfunction, right? Or an eigensequence if you want to stick to the discrete time terminology. Now z, I told you z will have magnitude as well as um, um, an angle or an argument. Yeah. So if you limit yourself to a unit absolute value, yeah, you remain on the unit circle, right? This is like you're remaining on the unit circle one. Then a simpler version of this observation is this: that you apply a complex sinusoid, right? And all the system does to it is that it is the same sinusoid but modified in such a way that it gets multiplied by a complex number. Because it's a complex number, it will have a magnitude and it will have a phase. So all the LTI does to this signal is that it changes the magnitude and it changes the phase, right? And interestingly, because now this was also the case in continuous time, but because this is a discrete time sinusoid and this is periodic, and when a discrete time signal is periodic, you get a different kind of repetitions. So this h of omega is also periodic as a consequence of that. This periodicity is actually carried over to this. So what you need to remember is that when you have a discrete time system and the transfer function of a discrete time system will be a periodic function. That's what you need to do. And next time we will see how can we exploit this. Because we don't want a periodic function. Why? Because we cannot store a periodic function. So we'd like to do something similar to DFT in the next lecture, right? So अभी आप attendance लगाएं और if there are any questions you can ask me. ये LTI वाली चीज आप पढ़ लें, इसमें कोई नई चीज नहीं है, ठीक है? The only new thing you will hear is the filtering, but filtering is something I already told you in continuous time. ये बताएं डॉक्टर एरम, आप ऑनलाइन है आज?
यस सर, ऑनलाइन हूँ।
अच्छा, तो आप जरा अपना बताएं ना अपडेट, क्या आपका लेक्चर हमारा अभी क्या आउट ऑफ सिंक है, हम क्या सीन है?
सर मैंने जो है वो डिस्क्रीट टाइम फोरियर ट्रांसफॉर्म स्टार्ट करा दिए थे, उसकी प्रॉपर्टीज कराई हैं कुछ मैंने।
अच्छा अच्छा, ठीक है।
जी, मैंने एक्स्ट्रा क्लास ली थी ना, तो इस वजह
हाँ
से।
ठीक है ठीक है, तो इसका मतलब है अगले लेक्चर में फिर DTFT कराऊंगा फिर मैं।
जी सर।
ठीक है ठीक। और वो जो लैब इंजीनियर्स हैं उनके साथ कोई बात हुई है?
सर उन्होंने मुझे वही डिस्क्रीट टाइम का भेजा था, वो कह रहे थे कि हमने डॉक्टर मुख्तार को दिखा दी है वो कोई प्रोजेक्ट जो था, तो वो उन्होंने मुझे
प्रोजेक्ट तो
दिखाया
ठीक
था।
है, प्रोजेक्ट तो वैसे भी उन्होंने अभी बाद में करना है।
जी सर,
लैब
उसके अलावा भी
के
उन्होंने कुछ नहीं
लैब
मुझे
के बाद,
भेजा।
हाँ ठीक है।
जी
क्योंकि ये जो आपके सेक्शन में अगर ये DTFT करते हैं ठीक है, मेरे सेक्शन वालों को DTFT अब समझ नहीं आएगी ना।
जी सर, अभी लास्ट टाइम तो उन्होंने जो है ना सिंपल डिस्क्रीट टाइम स्टार्ट किया था सिग्नल से सिस्टम पे।
अच्छा अच्छा, ठीक
जी
ठीक ठीक हो गया। बाकी स्टूडेंट्स कोई क्वेश्चन है तो आप बता दें।